going to be focusing on a video guide for designing a common emitter amplifier circuit. We're going to be doing this with a single BJT transistor and a few other discrete components. So the goal of this video is to show how to create the common emitter amplifier, and in our case we're going to be creating one with emitter and collector currents of 1 milliamp, adjustable gain with a minimum gain value of negative 10 volts over volts. Negative because this is an inverting amplifier. We're going to accomplish this by biasing the BJT transistor with a voltage divider biasing network. In this video we're going to be going over the theoretical reasoning behind the component value choices, and then we're going to jump into LT-Spice and simulate the circuit and see if our component choices give us the circuit behavior that we want. In the theoretical section, I'm going to be breaking down component by component how I came up with the value for each component. So we got the emitter resistor, the biasing network, collector resistor, all that stuff, and then we're going to go into some of the internals like RE prime, which is the transistor's internal resistance, and we're going to use input and output coupling capacitors to remove the DC bias, and so that the AC signal doesn't interfere with the DC biasing of the circuit. This is an adjustable gain amplifier, which means that we have a branch in the emitter in parallel with the emitter resistor that has a capacitor and a resistor, or a potentiometer rather, and tuning the potentiometer basically allows for us to have gain values much larger than our minimum gain, but much less stable to variations in beta. And finally, we're going to calculate the maximum and minimum gain of the amplifier. In the simulated section, we're going to be confirming the DC bias points to ensure that the transistor is in the active region, because when it's not in the active region, we're not amplifying, so it's important that we stay in that region. We're going to confirm the emitter and collector currents, choose the amplitude and frequency of the AC signal, just so that we can see what's going on, connect the AC signal, trace it around, make sure that everything looks the way that it should, and then to test the limitations of the circuit, we're going to sweep the gain resistor and the load resistor. Sweeping the gain resistor is going to show us, first the different values of the gain, but also how, when the gain becomes very large, how the output is affected. And sweeping the load resistance is going to demonstrate some of the limitations of the circuit as it relates to load values. So I've chosen to use a 2N5088 NPN BJT transistor. This isn't this is not a special transistor. Any NPN BJT will work in this configuration. VCC is just the rail voltage, meaning that it's the maximum voltage that our amplifier will be able to output. And diving into it, the emitter resistor, we come to that calculation, or the result of the calculation, by saying, okay, we assume that we have the voltage at the emitter, and we assume that that is 1 volt. And then we know the current that we want is 1 milliamp, so we can use Ohm's law and solve for the resistance. So VE divided by RE is equal to the current. Solve for the resistance, we find that the emitter resistor value that's appropriate is 1000 ohms. Next is R1 and R2, which are the voltage divider biasing network, which goes to the base of the transistor. R1 is the upper one, and R2 is the one that is connected to ground. So first we choose R2 between 1 and 10 times RE. In this case I've chosen 5.5K. And then you use the voltage divider calculations, VCC times R2 over R1 plus R2. And you set that equal to the voltage that you want at the base, which in our case we've already assumed the voltage at the emitter is 1 volt, so we assume that the voltage at the base is 1.7 volts due to the diode drop across the base emitter junction. So when we solve for R1, we find that the value is 43K, but I don't have a 43K ohm resistor, so I chose a 47K. And in this case, it's not going to affect the outcome too much, and it's okay to well, I don't want to say it's okay to fudge the numbers a little bit, but in this case it is. It just means that we'll see a slightly different, slight variations in the voltages we might expect to see based on the calculations. But for the collector resistor, we say, okay, we know there's 15 volts VCC coming in the top, and we want a gain of 10. So if we wanted 10 volts at the output, we would want 15 minus 5 volts divided by the resistance, because basically we can use Ohm's law. Voltage divided by resistance equals current. We know the current and we know the voltages, so we can solve for the resistance. In this case, we find that the resistance is 10,000 ohms. Our next goal is to find the values for the capacitors, the coupling and bypass capacitors that we're going to be using. But first we need to find the transistor's internal resistance, which is Re prime. We use this by using the equation Vt divided by the quiescent current to find Re prime. Vt we can assume is 25 millivolts at room temperature, but this does change with temperature, but we're just assuming room temperature. And then Iq is the desired current, so for us that's 1 milliamp. So we look at that and we just divide 25 millivolts by 1 milliamp and we come out with 25 ohms as the internal resistance of our transistor. So for finding the values of the coupling capacitors, we use the formula C is equal to 1 over 2 pi times the cutoff frequency times R. So in our case, that R is the complicated part, where basically you say, okay, looking in terms of AC, so any voltage, DC voltage source is actually a ground, what resistance do we see? So we have R1 and R2 in parallel, and then that in parallel with going through the transistor, we have the emitter resistor plus the internal resistance of the transistor multiplied by beta. And the result of this, when you do all that out, all the parallel calculations, you get 677 nanofarads, which I rounded down to a half microfarad, just for simplicity's sake, and that's the component value which I have. For the output capacitor, you do a similar calculation. And by the way, the 50, that's just a cutoff frequency, which I chose somewhat arbitrarily, which is why it's okay to just adjust it, because we're going to be filtering DC whether or not that's slightly, 677 or 500, same thing. For the output capacitor, we're looking at the same equation, 1 over 2 pi times the cutoff frequency, which in this case is 50, but this time the resistance value is different. It is the collector resistor in parallel with R1, in parallel with R2, in parallel with the emitter resistor, those three things in parallel multiplied by beta. And this gives us a result of 355 nanofarads, which I rounded up to 0.5 microfarads, which is the same value as the input capacitor. Just for simplicity's sake, I said, let's make them the same thing. So next we're focusing on the adjustable gain branch. So for the resistor in there, we want something, basically an arbitrarily high resistance, and then that can go down to resistance as low as 1. So I chose a 50,000 ohm potentiometer because that's what I had on hand. You could go higher. I'm sure at 50,000 ohms it's slightly influencing the gain, but we're not worried about that. But to determine the capacitance value, you use the same techniques as before, but when you do it, you say 1 over 2 pi times 50, but then we just do 20, so Re prime plus the value of the gain resistor, which at the lowest value would be 1. So we get 122 microfarads, which I've approximated is equal to 94. Based on the capacitor values that I have on hand to build the circuit with, this is the most practical value. Next we're moving on to the gain of the amplifier. So to calculate the maximum gain, we divide the collector resistor by Re prime, because when the gain resistor is at its minimum value, we're pretty much just going to be seeing Re prime. So RC divided by RE prime, in this case, gives us a gain of negative 400 or 52 decibels. For the minimum gain, we divide the collector resistor by RE prime in addition to the emitter resistor. So in this case it's negative 10,000 ohms, or 10,000 ohms divided by 25 plus 100. So this gives us a gain value of 9.75 or 19.8 dBs. Alright, so we've moved on to the simulated section of this video where we have the circuit schematic here with all the values we found in the theoretical section. Okay, so we're going to check out, I've just run the simulation of just doing a transient analysis, 5 milliseconds, and we're going to look at the voltage in the base, which is our voltage divider, and that is giving us a little more than 1.5 volts. And it's because there's about a 0.6 to 0.7 drop in the transistor, we should have, I guess, a little less than 1 volt in the emitter branch. Let's check it out. So yeah, we have 0.96 volts in the emitter branch. It's a little less than what we would like, but this is a compromise that I had to make with the component values because there's only certain values of resistors out there. So now looking in the collector branch, we see that we have a little more than 5.5 volts. In the calculations we were shooting for 5, but again, that was a little offset by the having to choose practical values for resistors. So now we're going to look at the current going through the emitter and the collector resistor. So starting with the collector resistor, we look here, our goal was 1 milliamp, we have 0.94 milliamps, and then what do we have here? We have 0.945, so very similar. As you can see, when we do calculations we assume the current in the emitter and the current in the collector are essentially the same. We can see there is a little difference here, but they're essentially the same value of a little less than 1 milliamp. We're okay with that. So now we're going to choose the value of our AC signal. So we'll go in here and let's say do 1/4 volt just so we don't overshoot. And we'll do 1000 hertz, so we're well over the cutoff frequency that we've chosen, which is pretty much just for DC. So we got that, and we will connect this branch up here and run. So let's just take a look at our input signal first. You can see it's just 250 millivolt AC, 1000 hertz. Then we look here, same signal, but it's biased a little bit at our 1.6-ish volts. You go down here, you can see it's about 1 volt. Then the big one at the output is that we have it amplified now. So it's easier to see the relativity of how much it's amplified when I look on the other side of the coupling capacitor. So what I'm going to do is I'm going to look at the input signal, set it 0, so it's right at the center, so we can see 250 millivolts. And then we probe here, and we can see 2.5 volts. So that is an amplification of 10, but it's actually amplification of negative 10, because if we look here, while this is at its peak, this is at its minimum. So the output is phase shifted by 180 degrees. Alright, so now we're going to take a look at what the gain resistor branch is doing. So what I've done is I've changed the value of this gain resistor. Well, I've connected it and I've changed the value to this R2, which is referenced down here in this SPICE directive, which is going to step in a decade sweep this parameter R2 through a range of 1 ohm to 50,000 ohms. So we can see, and that's essentially just going to be altering the gain from the minimum to the maximum, or at least 50K is the value of the potentiometer that I'm going to be using in the actual circuit, so I figured I'd set that as the cap. So let's run this here, and let's probe the output. So we can see, so we have, for the high values of gain, we're capped out at 15 volts. You can't go any higher than that because that's our VCC. At the bottom here, you see we're not going to 0 volts. We actually start to lose the signal around 1 volt. So if I just zoom in here, you can see, yeah, around 1 volt, we're out of the range of operation. And there's some variance there with the different values of gain. But essentially, what is happening here is in this lower, for the transistor to be in the active region, the voltage in the collector must be at least around 0.2 volts greater than the voltage in the emitter. When we have these big gain values, we're getting down to a place where we're no longer going to be in that region. So when it's trying, oh, I got to go down here, but then it's actually not amplifying anymore. It's not acting in the active region, so we don't see that value reflected in the output. Alright, so what I've done now is I've changed the circuit a little bit. I've changed this gain resistor back to the 50K, the max value, so it doesn't interfere with the gain of our circuit, or maybe, to a tiny degree, but not anything substantial. But what I have done is I've taken the load resistor here, which was before fixed at 1 mega ohm, and I've changed it to a value of R1, which down here in the SPICE directive is a sweep value, a decade sweep from 1 to 2 mega ohms. So we're going to see pretty much a full range of loads and what effect that has on the circuit. So let's check it out. So if we look at the output voltage, you can see that at the high values of load resistance, we're getting the 2.5 volts that we expect. But there's a significant amount of values between the max value and the minimum value in which we're not seeing the output that we want to see. So with these lower, let's just see, for example, this is risky, but I'm just going to try and change this. Let's change this to 10K. Yeah, we see that's not 2.5 volts, that's 1.2 volts, a little more than that. So if I do 2 meg here, we're seeing the full 2.5. If I do there, but basically we don't have that much, we have to have a high value here, otherwise we're going to be in trouble and not actually get the gain that we want to see at the output.